I'll begin with a word of prayer. So, dear Heavenly Father, we thank you again for this opportunity to meet together and study your creation. Help us to just understand a little bit more about norm spaces and perhaps Banach spaces. We'll see. In your name I pray, Lord Jesus. Amen. So, last time we, mentioned that given a norm, you can define a distance function, right? And with that distance function, we defined open, closed ball, sphere. We proved that any two norms on a finite dimensional vector space are equivalent, right? And then, so I guess I'll just start with the definition, which is that S, a subset of a normed space E, is called open, right? If for every, let's say, x in S, there exists epsilon greater than 0, for which the ball centered at x of radius epsilon, which, by the way, I'll just write out what that is. That's, y in E, such that the norm of y minus x is less than epsilon, right, as a subset of S, right? So that's an open set is one for which each point in the set you can find a open ball contained around that point inside the set. And then if E minus S, which I think your book uses E like this. I don't like that notation. I use minus for set difference. Is open, then S is closed. So to say a set is closed means that its complement is open, all right?
So I meant to ask, when we're talking about notions of these norms, it seems like a metric. It seems like how we define metric in topology. But it's not quite the same, is it?
No, I think the metric we defined in topology is a more general concept, but there are specific metrics which we can induce a metric from the norm. So,
okay.
But
Norms are kind of a subset of metrics.
There are some metrics which can be realized as the difference of a norm, but not all, because, well, for example.
Yeah.
For example, you can take an arbitrary space, right? And you can define the distance between 2 points to be 1 if they're not the same point, and it to be 0 if they're the same point.
Yes.
That defines a metric on an arbitrary set. And
Discrete, right?
yeah, we call it the discrete metric. The topology which that induces is in fact the discrete topology. Have you guys defined topology yet?
No, except for that.
Okay, that's fine. Dr. Sperano tends to take his time, and that's cool. So, all right, so.
Not formally, that is.
What's that?
Not formally, that is.
Not formally. Oh, cool. What's that?
What's the book he's using?
He's using Moncrief's.
Yeah.
Okay.
Yeah. All right, so then we have examples. So I'll just, I'm not going to prove these, but I'll just state them. Number one, open balls are open, closed balls are closed in the technical sense defined, like we defined open and closed ball last time. If you take those sets, you can prove that those in fact are open sets and closed sets, and also spheres. The sphere is closed. And then two, this is his example 1.3.19. He, he's working in the continuous sets defined on a closed bounded subset of Rn. So continuous functions on a closed bounded subset of Rn. Remember, we had the norm of f to be equal to the max for x and omega, the absolute value of the function, right? So we're looking at either real or complex valued functions on a closed bounded subset of Rn that defines a norm, and then he gives this like laundry list of sets which are open and closed. Like it's like if you've got a positive function, for example. So okay, well, you know what? Once he writes that, so he something a little funny going on in example 3.19. 8 of the things he writes here assume, well, okay, fine. Just whenever you write inequality of elements, you're talking about real numbers, right? We can't write less than or greater than for complex. So, you know, when he says lambda is an element of C, for like that last thing, okay, fine, but you know, he's thinking of G being complex valued in the last statement of example 3.19, but he's definitely thinking of G being real valued in the first statement of the second part of example 19. So just beware of that. Like, I'm not telling you anything terribly exciting. Anyway, the point is, if you have a set like this, so G and C omega such that G of x is less than f of x for all x and omega. I'll just write 2 of these, okay? Like that is open, is an open set. Whereas in contrast, if you had like G and omega and C, G and this, the set of continuous functions on omega, right? Such that G of x is less than or equal to f of x for all x and omega, then this is closed. All right, and it's the same is true if you replace with, you know, basically the other 2 examples are like turn the inequality around, you know, and it's still open, it's still closed, and I guess I'll write one more. This is the one that I thought was interesting. G in continuous functions on omega such that G of x naught is equal to lambda. So here x naught fixed point and lambda is a complex number. He says that this is closed. It's a closed set. So like I said, I think like roughly speaking, an intuition that usually serves me well is if something's defined in terms of equality, it tends to be closed. Whereas if something's defined in terms of inequality, it tends to be open. But as you can see, that advice is somewhat perilous. If you're like, you get to this and you're like, but it's both, you know? So the equals wins. I don't know. Okay, so then theorem 1.3.20 says the following. So now we're really getting ahead of your topology class, I'm afraid. You'll forgive me, but don't worry, you'll do it. Union of, what's that? Union of any collection of open sets is open. The intersection of finitely many closed sets is closed. And then C, the union oh, well, this is union of finite number of closed sets is closed. And he leaves that as an exercise, a homework exercise for you guys. So here I'd assume that the homework exercise is supposed to be done in, you know, in the context of a norm, and like a, you know, a norm induced, in a normed linear space, right, in the topology we're looking at here. Oh, goodness gracious. The intersection of any collection of closed sets is closed, and the empty set and the whole space are both open and closed. Oh, I thought I was done writing. And then I turned the page. So D, arbitrary intersection of closed is closed. There, I'm going to abbreviate it like that. And then E, the empty set and E are both closed and opened. All right. So actually, spoiler alert for your topology class. Basically, you can take A, trying to remember.
It's finite closed, infinite open, and empty set and the whole set.
I feel like I may have written these down wrong, right? The intersection of finitely many open sets is open, I think is what I wanted.
Yeah.
Sorry, my bad. So the first two, like A and B and E, is the standard definition of topology. Arbitrary unions are open, finite intersections are, finite intersection of open is open, and the whole space and the empty set are open. But you can also define a topology in terms of closed sets if you want. And then you have, you know, intersection of finitely many, the union of finitely many closed is closed, and the arbitrary intersection of closed and closed. So like, which one gets the arbitrary flips, whether you're going to use open or closed as your like primary idea. Let me not teach topology in here, sorry. My apologies.
My apologies.
My topologies. That's on you, Audric. That was your fault right there. That's not on me, that's on you. All right, so I should have written none of this, because none of this is really analysis. This is all just topology.
Oh, this next theorem is going to help them out.
Yeah, the next theorem is analysis.
6 chapters for minute.
All right, so next up, now we trade this, you know, sort of ethereal idea about open balls for something much more concrete. A subset S of a normed linear space E is closed. All right, if and only if x1, x2, xn in S and xn converges to x implies that x is an element of S. So what this theorem is saying in words is simply this: a closed subset is one for which every convergent sequence in the subset converges to a point in the set. All right, so let's look at the proof, right? So he begins by supposing, suppose S is a closed subset, And suppose you've got, xn converges to x, right, where x1, x2, is an element of S, right? And then towards a contradiction, what are we going to do? Yeah, suppose X is not an element of S, right? So we're assuming S is closed, right? So thus, X is an element of, E minus S, right? So X is outside of S. And this is open, right? Which means what? So therefore, there exists epsilon greater than 0, such that the ball of radius epsilon centered at X is a subset of this, the exterior of S. Yet, the norm of xn minus x is going to what? I think it helps to draw a picture in this kind of problem just for the sake of organization. Like our set is S, right? And we're supposing that we've got this sequence, and somehow it converges to this point X out here, right? And so since the exterior is open, we've got this epsilon ball out here, right? And that's outside the set. And yet we're saying that the distance between x and xn is going to 0 so that's a contradiction. It's an intuitive contradiction. I don't quite see it on paper, though, honestly. What exactly is the contradiction?
Because there exists game where the norm is greater than epsilon.
I think what this says, right? What this says is that xn is an element of E minus S for n sufficiently large, right? Because this right here, right? And I think that's the contradiction, right? Because we're assuming that the sequence is in S, right? So we're assuming the sequence is in S, and yet we're saying that if you go far enough out, you can find points outside of S, which is not legit. So that's a contradiction. Therefore what? Therefore x is an element of S, right? And then the other direction, we suppose xn goes to x for x1, xn in S implies x is an element of S, right? We suppose that that's true. We want to show, our goal is to show that S is closed, right? So we let me follow the book because I feel like we should just pick a point. Oh, well, he does by contradiction again, so if he does that, that's probably for a reason. My inclination is just to try to prove it directly, right? I mean, we could try that and see what happens. To prove it directly, I would try to prove that the complement of S is open, right? So I would let, Z be an element of E minus S. And then I'm just kind of stuck, right? I mean, I don't know what to do. I'm not sure what to do past that. So let's not go down that path because, the direct path here is not helping me. So it's not helping you. So what he does is he said, if S is not closed, which would be a contradiction, right? He's working towards this is proof by contradiction again, right? So suppose S is not closed, then what happens? Well, if S is not closed, then E minus S is not open, right? Thus there exists X, an element of the complement of E by S, such that what? Say again?
Is it a sequence? Convergent X outside of the...
Well, it's not open, so that means there has to be a point such that every open ball around X is not a subset of E minus S, right? Which means that the ball of any radius epsilon X is not a subset of E minus S, right? For all epsilon greater than 0. But what's another way to say that? In other words, that's saying that there is a he says that says every ball X epsilon. So this. What'd you say, Jacob?
I say there's elements in the ball that, that aren't.
So it contains points inside in S, right? And then what he says, he's like, okay, so thus we can find x1, x2, da 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 in S, such that xn is an element of hence there exist x1, x2, da 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 xn. Well, he doesn't do the xn, he just says da 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 in S, for which xn is an element of the ball. So he's going to pick a particular epsilon here, and this is pretty much what they always pick. Like when these kind of constructive arguments, they always just put epsilon equal to 1 over n. I'm noticing this again and again and again. This is like the way we prove things in here, yeah? And okay, so let's go through this again. Does that make sense that we can construct a sequence like this? Because we've got this point x, right? And so for every epsilon 1 over n, we can pick a point, right? And more than that, what do you get about the norm of xn minus x? It goes to 0, right? Because as n goes to infinity, that shrinks to just to the point. Right? So what do we have then? We've got a sequence which converges to x. Right? So in other words, we have a sequence in S which converges to x. And then what's the assumption? By assumption, if we have a sequence that converges to x of points in S, it follows that x is an element of S. Right? But what is that? Well, that's a contradiction, right? Because oh man.
Yeah, we said that there exists x and e minus s, so we have x and e minus s and x and s. We're having element in a set.
Oh, yes. Sorry, I've got so many different things written on the board, I've lost track of which one is the starting point. That's the starting point, right? So this right here, yes, this x we're talking about has been, yeah, so this up here is the supposition of this part of the proof, right? That's not the x we're talking about. This is the x. We picked this x. We looked at it since it's, we found this, constructed the sequence using that, and then that forced us to then say x is in fact an element of S, which of course is a contradiction. All right, so. Right, because to say that x is an element of E minus S is to say that x is not an element of S. All right, I'm tired of talking about this one. Can I go on? But this is important, right? Because this is how we test for closed using sequences, right? Is every convergent sequence in your set converging inside your set? If that's the case, you have a closed set. This is how we define closed sequentially. Now, this method of proving things are closed is not available to you in many examples in topology, because in topology, sequences are not enough. All right.
This kind of only holds for norm spaces, then the use of sequences.
For norm spaces or more generally metric spaces. Like this is, you notice that we didn't really use the norm anywhere here, right? We've just used really the ball idea.
Yeah.
So, but yeah, definitely for norm spaces. Definition. I gotta stop using this marker. That marker's trash. For S, a subset of E again, the closure of S denoted in this book CLS. It's just equal to the intersection over a closed, let's say C, such that S is a subset of C. In other words, it's the intersection of all closed sets which contain S. And then theorem, closure of S is in fact just equal to X and E such that there exists X1, X2, in S for which xn goes to x. The proof is left as an exercise. Man, these exercise proofs are really saving me a lot of time. I'm very thankful for them. But this is, I think a little bit less intimidating. The intersection of all closed sets which contain, a given set, that's kind of hard. But if you just think about, it's the set of all possible convergence, all limit points, right, for convergent sequences, okay, that's the closure. Example. And this example is telling us something that's kind of technical and interesting, and probably something that wasn't actually proved in the course where it should have been proved. So the Weierstrass theorem says every continuous function on the closed interval from a to b, all right, can be uniformly approximated by polynomials. All right. So what's that saying? Like, you can find a sequence, right? P1, P2, ... These are polynomials. Polynomials on the closed interval from a to b, such that the norm of P1 minus f, Pn minus f rather, goes to 0. And here that's the that norm we talked about. Remember the what was it? Like norm of, so it's like norm of Pn minus f is max of, I want to say it's the max of like t and a to b of the absolute value of like Pn of t minus f of t, if I remember right. He called it the uniform convergence norm, right? So here f is an element of just the continuous functions on a to b, right? And what he says, that theorem, Weierstrass's theorem, can be understood to say here in terms of our current language, is that the closure, right, of the set of polynomials on a, b, my notation, I just invented it, okay, is in fact the whole kit and caboodle. He just says it in words. The closure of the set of all polynomials on a, b is the whole space. Continuous functions on a, b. This is Weierstrass's theorem. Definition. A subset S of normed linear space E is called dense in E if the closure of S is equal to E. I feel the need to add parentheses where he doesn't have them, so you can take it or leave it, but, I like my parentheses. All right. He gives this another example, polynomials. Okay, well, the polynomials are dense. That's what this says. Okay. His next example is set of all complex sequences of complex numbers that only have a finite number of non-zero terms is dense in LP. So his next example so you could say P equal to, you know, well, let me not get dragged into it at the moment, actually. Well.
It's basically just what you wrote.
Yeah, I'm trying to think of a different notation here. What is LP? So it's like, yeah, like complex sequences such that what? Some, right. So he's talking about polynomials in there in the sense that we're looking at Zn such that the sum over, you know, well, such that Z sub n is not equal to 0 for finitely many n. It's polynomials. If you have sequence with, you know, I mean, I can think of it in terms of polynomials. I don't know. I mean, there's the sequence, there's the sum of the sequence, so it's like, it's a little bit dangerous what I'm saying, but anyway, these are allegedly dense in LP. There's so many other things to say about things that are dense. A more interesting example, which might be out of place here, but I'll give it anyway. You guys remember, if we look at rational numbers, that's a subset of the real numbers, right? And any real number can be written as a sequence of rational numbers, right? Like, so for any C in the reals, there exists Cn in the rationals, right? Such that Cn goes to C. So every real number is either just already irrational or it's a limit. I mean, if the real number is already a rational number, then you can take the constant sequence, and it's therefore the you know, limit of a convergent sequence. So the fact that this is true, and if you don't believe me, you could just take the you know, truncated decimal expansions of the real number, just take more and more and more decimal digits that will converge to the real number. So if you have decimal expansions, this is super easy. Now, some people would say that's like really abusive in terms of a proof, but there you go. Anyway, my point to you is that the closure of the rational numbers is the real numbers. And the rational numbers are dense in the real numbers. So, okay, then the next theorem up is that, you know, a list of equivalent conditions for dense. So what are other characterizations of the following are equivalent. So A, S dense in E, B, for every X in E, there exist X1, X2, in S, such that Xn goes to X. I think I just used that, didn't I? in my example. Uh-oh. Yeah, we're okay. If my laptop was on the floor, we'd know I did it. And then C, every non-empty open subset of E contains an element of S. Every non-empty open subset of E contains element of S. So these are convenient ways to characterize density. All right, and again, the proof is an exercise. This has been so relaxing for me today. All right, let's go on here. Compact. Definition. S, a subset of E, is compact. All right. If every sequence Xn in S, all right, now this is a little slippery, contains a convergent subsequence whose limit belongs to S. So this is what's known as sequential compactness. All right? So his first example is that really it's more of a reminder, it's not so much an example, but is that in Rn or Cn, subset is compact if and only if it's closed and bounded. And then, of course, that begs the question of what do we mean by bounded, right? So let's define bounded. What does bounded mean? Definition: S, a subset of E, is bounded if there exists, let's see here, R greater than 0, such that S is a subset of the ball centered at 0 of radius R. So, I mean, that's not my usual definition of bounded, but yeah, it works. I usually just think about there existing a ball that surrounds it. I don't insist my ball be centered at the origin, but you know, logically speaking, if you can do it around some other center, you can always do the one from the origin to get out that far. So it makes sense. Yeah. Yeah. And he says it's easy to show it's bounded if and only if. So here's a claim, which I'm tempted to try to prove. He says S bounded if and only if the norm of lambda n xn goes to 0 for any xn in S and scalars lambda n which are converging to 0. He says it's easy to show. All right. So do we want to take the bait and try to prove it? What do you guys think?
You look at that, so I can look at later.
I'm willing to try a direction. How about that? I'll take a stab at. Let's suppose. Let's suppose that we have this data over here on the right-hand side. Okay, so like, let's look at this direction for a second. So suppose you've got all this, yeah? And then suppose S is not bounded. Then the idea would be to show that it is bounded as a consequence of this data, right? So I would, I probably would do something like look at lambda n equal to 1 over n, right? Those are going to 0. And we also have like the norm of 1 over n x sub n goes to 0 for all xn in S, right?
Now we just have to find a convergent subsequence, which one it belongs to S.
Oh no, there's no we're not in the compact stuff yet. I mean, we're just trying to show, I'm just trying to show like
So it's bounded.
it's bounded, I don't know right offhand. I mean, there's got to be a simple argument here because he says it's clear, but when I read it, it seemed intuitive to me. So, But anyway, there's something to think about there. So, if that's a service I can provide here to kind of, I don't know. So these books sometimes have this habit of throwing the sentence in here, which makes you feel like, as like a reader, that like, oh, I should just see this, but I don't know. I'm not the smartest dude in the world or anything, and I haven't spent a lot of time on this yet, but I feel like there's some thought that's required here. Okay, let's go on. That is, I think I'm pretty sure that's a homework exercise. So, all right. So the fact that it's closed and bounded, it's a closed and bounded subset of Rn, if and only if it's compact. That's special to Rn. All right, let's look at this this theorem here. And here's the theorem. Compact sets are closed and bounded. Now that does not presuppose finite dimensions, right? So let's look at the proof of this. Assuming I have time. Let's see here. I think I have time. All right. Where was I? It says let S be a compact subset of a norm space E. All right. And let x1, x2 be elements of E, and xn converges to X. Thus, xn contains subsequence. Let's say x sub pn, all right, which converges to some y in S. All right. So what are we trying to do at the moment? We're trying to prove that compact implies closed. All right, that's what we're on right now. So what we're doing is we're taking an arbitrary sequence which converges, right, inside this set. We'd like to show that the limit of that sequence must be in the set. So towards that end, we're using the sequential compactness, which says that there exists a subsequence which converges to a point inside the set. But then we're going to use a theorem that a convergent sequence has to converge to the limit of any subsequence. So, you know, and so I would, you know, but xn converges to x, thus x is equal to y is an element of S. And what's that prove? That proves that an arbitrary convergent sequence in our set converges to the point inside the set, which is to say that it's sequentially closed. So that's half of the battle, it's closed, all right? Now, so admittedly, there's a gap there. I mean, but hopefully that was a gap which was already made clear in real analysis, right? If the limit has an, if you have a, right, if you have a sequence which converge, any subsequence must also converge to that same. And in fact, its principal use was in proving that sequences don't converge, right? So if you can find two different subsequences which differ in their limits, then that proves the sequence is not convergent. In fact, that's something I really we should all be teaching calculus too if we were doing our job, but that gets de-emphasized in the introductory books, and as such, I've never taught it.
If you have a convergent sequence to subsequence, the limit of the subsequence has to converge to that same point.
Yep. Yeah. Let's see here. So to prove that, you'd need to know what the definition of subsequence is, right? So the definition of subsequence is that there exists an increasing function on the natural numbers whose composition with the original sequence then gives you the subsequence. So like, you know, it could be you're just picking up even terms in the sequence for the subsequence or whatever. The important point is this Pn, right? Pn is, let's say that's equal to P of n. P is a mapping from the natural numbers to the natural numbers, and it has to be increasing. That is the definition of subsequence. Is that you know, you have to, there has to be a direction. You have to go out in the sequence. You can't do a subsequence where you're sampling doop, 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 doop. That would be something else. We're not allowed to do that. It has to be increasing. Oh, what's left? We need to show it's bounded, right? So he says, now suppose S is not bounded. All right. Then there exists sequence x1, x2, da 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 in S such that what? Such that the norm of xn is greater than or equal to n for all n in n. Right? If it's not bounded, you got to be able to find points beyond n in distance. And he says clearly x sub n does not contain a convergent subsequence. So therefore, S not compact, right? Which of course is a contradiction. So we learn, in fact, S must be bounded. All right? But be careful here. This implication. So like, I don't know. It's funny to me. I feel like these two proofs, to me, they feel easier than the thing he says is clear. But maybe that's just because I see these ones and I don't see the other one. I don't know. So his example 1.3.32, I will admit I don't understand. So he's got the continuous functions on 0 to 1. All right? Oh, no. So he points out the closed unit ball. All right? It's a closed and bounded set. But it is not compact. And the reason it's not compact is, he says, if we look at xn of t equal to t to the power n, then xn is an element of the closed ball centered at 0 of radius 1 for all n and for all natural numbers. All right? And he says clearly, and this is the clearly part's what part that gets me. Clearly no subsequence of xn converges.
Is T in the closed interval? Yeah, is T in the open interval 0, 1? Yeah, so when that converts to 0.
Okay, so yeah, let's try to digest this example. That would be good. Can I erase the proof? I think we're from that. All right, so are we all? Yes, I mean, well, t to the n, yeah. Let's see here. So first of all, we agree it's closed, and we agree it's bounded, right? That much is clear? Because like it's literally contained. I mean, you could look at to see it's bounded. Just notice that. Let me just start out by saying positive things, which are easy.
Well, if T is less than or equal to 1.
Right. This is definitely true. So hooray! You know, it's a subset of that, so it's bounded. Way. All right, it's bounded. It's closed because it's the closure, right? So closure is closed. This is also a homework problem. Great. Fine. So, do we also agree that xn of t equal t to the n defines a continuous